Alright folks, today we're going to cover all of Chapter 5, and it focuses on bivariate data, which means we're going to have two variables that associate with each other. And how we're going to measure that association is with a visual, a scatter plot, and also talk about some of the features of, specifically today we're doing line of best fit, so some of the features that measure correlation with a linear relationship. So first, we're going to talk about the patterns in the data on a scatter plot. So a scatter plot just has your ordered pairs plotted on a graph, and we're looking for a general association of a pattern going up or a pattern going down. And then we'll talk about the line of best fit, or a trend line that kind of cuts those points going through the middle, either in an increasing fashion or decreasing. And we know the general form of a line, y equals mx plus b. We've got a slope that we need to talk about and a y-intercept, some starting point that we need to talk about. We may have outliers, but the nice thing about Excel is it's going to find that line of best fit that best fits the points based on the data that we have. So first up is a measurement of correlation, and it's called the correlation coefficient. It tells us how the two variables relate to one another, and specifically it talks about the degree of linear relationship. So we're only going to talk about lines for this chapter, but correlation coefficient only can talk about lines. So here's the formula, and some parts of this formula should look familiar to you. So inside here we've got this x minus x, or the value minus mean, divided by the standard deviation. So this whole first parenthesis deals with the z-score for the x value of some point, times then the z-score of the y value of that same point, and we're multiplying those two together. Then we do that for every single value in the table, add them all up, and divide by one less than the number in the set. Okay, so that's how it's calculated. Fortunately for us, Excel has a formula that will do it for us. What we're going to concentrate on more is how it looks and interpreting its meaning. So first thing is recognizing that an R value for us is only going to fall between -1 and +1, with those values meaning different types of correlation strength. So here are all the properties that deal with the correlation coefficient. First of all, it measures the degree of linear relationship, or how strongly our points are clustering around the line. Okay? If it's not linear, then we're not going to use R at all. Okay? It's always between -1 and +1, and a value near those ones means that we have a close to perfectly linear relationship. Whether it's positive or whether it's negative will tell us about slope, and if it's close to 0, then there's not really a linear relationship. Some other type of model might be more appropriate. Okay, so strength, here's what we're looking at, how tightly bound it is, just a visual. And then remember, we can talk about sign as well, whether they go up or go down. So on this number line, what I'd like you to do is add some notes here to kind of generalize those properties. So you can type this or write it, whatever's easiest for you. Okay, I'm going to write it, but you may find it easier to just click the cell and type this in. So when we talk about perfectly linear, that's going to be our -1 and +1. So that would mean every single line, or every single point is on the line of best fit. That would be a -1 perfect. Over here, at a +1, is still perfectly linear, but it has a positive slope. So going up, every point is exactly on the line. 0 would be no linear relationship. And then on either side, here's my 0.5, something over on this side would be strong, positive linear. As I get closer to 1, it's stronger. When I'm closer to 0.5, it's more weak or moderate. Same thing on this side, -0.5. Okay, as I go this way, I'll have a strong negative linear relationship. Okay, as I'm closer to 0.5, it's moderate, and as I get closer to that -1, it's stronger. We're really not going to see numbers close to -0.5. We'll see at least like 0.8 and above. Okay, so as we increase, it's stronger, but this is really our moderate. And then in between 0 and 0.5 is weak, and maybe not appropriate to use. If we don't have any other option, of course, we'll go that route, but it's not really going to be doing much for us, as the point of a line of best fit is to predict values using the pattern from our original. So maybe linear wouldn't be the pattern that we're looking for. So what we're going to do is just place A, B, C, and D on this number line just for practice and the visual. So A is positive, and it looks like it's pretty strong because they're tightly bound. You could draw a line on there pretty easily. So this correlation coefficient, maybe it's 0.8 or 0.9, so it'd be over here. B is not quite as strong as the first one, and negative. So it's not as close to -1, but it is on that side. Stronger than moderate. C is not linear at all. That looks more like a parabola, so we're putting it near 0. And D, if you had to draw a line, it'd probably be positive, but it's not very strong. Okay, so D is somewhere in this moderate area. Okay, so that's kind of a visual for when you look through here of kind of what to expect for those R values. So what we're going to do is some examples, and we'll talk about actually calculating it with the values. So we have two variables, hours spent studying and midterm grades. Okay, so we've got 5 students. They spent 0, 1, 2, 3, or 5 hours studying, and then these are their grades on this midterm exam. So from here, we want to just calculate the correlation coefficient. We've got a table going left and right and a table in columns. You can do this with either. Okay, so what I want you to practice here is labeling. Correlation coefficient is the variable R. And over to the side, we're going to type correlation, and that first thing that pops up is it. It says array 1 and array 2. You do not need to put these in any specific order. That's just your X's and your Y's. I am going to have you put the Y's first for these, only because what we do down the road here will require us to go in a specific order. Correlation coefficient, though, does not matter which one is X and which one is Y. So looking at the table, as X is increasing by 1, Y is definitely increasing. So I have a positive slope, and a positive R value correlates to that. Then this number is very close to a positive 1. That tells you we have a very strong positive linear relationship. Okay, so what we're going to do is actually interpret this just for practice. Since R is positive, there is a positive relationship between hours and midterm grade. Okay. Then since R is close to 1, that relationship is very strong. Okay. And we can, of course, put this in one sentence, but I wanted to write them separately because are really indicating what the two things that we're working with here. One is sign and one is size, okay, or the magnitude closeness to 1. Okay, one thing I want to really emphasize here is a high correlation does not mean cause. Okay, so just because this was very close to 1 and there's a strong association between these two variables, it does not mean that the hours spent studying caused the midterm grades to be higher. There are other factors that could have played into that. You know, someone's a good test taker, someone is, you know, if they're regularly spending lots of time studying, maybe they're a better student in general and have good study habits. So one example here that really ties this in is an example of we have, as the number of weekly ice cream sales goes up, so does the number of snake bites each week. Okay, that doesn't mean ice cream causes snake bites to go up. There's this other factor, sunshine, causing maybe the other two to increase. Okay, so there's this other factor that could be explaining the relationship between the two variables increasing. And so that right there is called a confounding or lurking variable. So a confounding variable means a variable that is explaining this phenomenon that we're aware of, and a lurking variable is when we aren't really sure that of the cause. Okay, we don't know necessarily what that third variable or that extra reasoning may be. Okay, so confounding variable is some other cause, and if it's a lurking variable, we maybe don't know what that cause is, but we're not sure that the one thing we're seeing is the cause. Okay, so look out for those. Correlation is a relationship. It is not a causation. Now, there may be a good reason to believe there is one, okay, but suppose we think that's happening, but the correlation is near zero. That may indicate then there's no linear association, not no association in general. So here, if we talk about this, we only are going to have R when we're dealing with linear relationships, something like the first few pictures. But there are other models, kind of like what we talked about, the U-shaped, the parabola above. There are other models that may be appropriate. Okay, so we want to be careful when we're writing our interpretations in our sentence that we're saying no linear relationship exists for those situations with low R value, because there could be a good model, we're just not going to put a line on it. So speaking of lines, we're going to now actually get to fitting the line of best fit. Okay, from what you know from algebra, basic form is y equals mx plus b. With our book, a lot of the examples, you're going to see them mixed around in this order, where it's some number, the constant first, and then it has this slope value second. Okay, so that's something we're going to have to be careful of. Now, one thing I want you to take note of is the word they use here is regression. This regression is a fancy word that just means the model. And for us, it's going to be the line of best fit, or a linear regression, a linear model. Okay, so that just means the equation that we're using to model our data. So if we look at our model, we know our line of best fit that our Excel is going to give to us for us won't necessarily be perfect if our R value is not -1 or +1. So there's some amount of error. Okay, we just decided that if we have something closer to 1 and -1, it's strong, but we want to talk about error as well, the points that don't perfectly fit here. And that's going to be represented by the sum of squared errors. Okay, so here, the visual for this, there's a link for it, but I'm just going to kind of draw it on here. It's talking about the distance between each of these points to the line. And that's what this says, is taking the y value minus the y value from the line of best fit, taking that difference and squaring it. And we're squaring it so that we have a positive value. Get back here to my visual. So that we have a positive value for all of these. And we add them all up. The reason we want positive is I don't want this distance here and this distance here to cancel each other out by adding them. Okay, so we're squaring the number. Once we square the number, then we add them up. Okay, so we're going to practice on this next one with that. So it says, compute the sum of squared errors for this situation. We've got students' college GPAs and high school GPAs, and here's the value for us. So it tells us here that the estimated college GPA is equal to this formula, so it gives us this line of best fit. And this is a good practice to kind of get into. They indicate that the estimated college GPA is in the Y spot, so that's our dependent variable. And just put that here. And then our X is our independent variable. Okay, so a lot of times in the stats world, this is the response variable, and this is the explanatory variable, because the high school GPA could explain why the college GPA looks like it does. Okay, so what we're going to do is the sum of squared errors in a few steps. So the first thing is we want to do the predicted value from the line of best fit. Here's the Y values that actually happened, but we have an equation that predicts the Y values that could happen. So we're going to do predicted college GPA just beside it. And that comes from our formula. So equals, they gave it to us. Sometimes we're going to calculate this ourselves, 2.2922 plus the 0.1243 times the high school GPA, and we'll grab it. Then we can drag that down. And you'll notice these values have kind of a similar pattern to these values. Okay, not perfect, but there is some difference. Okay, that's the difference we're going to find for the next one. It says we want to find the squared error by doing the difference first and then squaring them. So this is just error, and I want you to make yourself a note. This is going to be predicted, or the actual, excuse me, minus the predicted. So equals, the actual college GPA was here, and then we're doing minus the predicted college GPA, and then dragging that down. Okay, go ahead and here, if yours is doing what mine is doing, go to your home and click wrap text so it gets out of the way of the next one. The next one is going to be error squared. And we're literally taking that error we just got and squaring it. Dragging that down. Okay, as you go through here, if you get a little behind, pause the video, rewind. The last step is summing these. So down at the bottom, let's write sum, and then do equals sum, all the way down. Okay, so this is your sum of squared errors. If it asks for that on Hawks, it's just looking for this process here. That's the total squared error in all of this. Now, one other thing I want you to pay attention to here is if they ask you to round, this one says 4 decimal places, so we're going to adjust that. And sometimes error is referred to as a residual, so I want you to write that note as well. So sometimes called sum of the squared residuals. Okay. So our Excel does that line of best fit for us, so we're going to do that on the next one. Okay, and the line of best fit by definition is going to have the least sum of squared errors possible. It will also include the average of the x's and the average of the y's by definition. Okay, that's called the center of gravity. What you need to know is how to find each of these 3 things in Excel to really be confident for this chapter 5. So the line of best fit, you need the slope and the y-intercept for, so we're going to do those next. And then the correlation coefficient is another thing that you'll be able to calculate using the table. So to start out with, we're going to do R, because that is what we have done before from up above. Correlation coefficient, remember, tells you how linear our association of our 2 variables is. So for what we're doing, we want to read context to decide which one's X, which one's Y, so that we know kind of how these relate for our independent and our dependent variables. says a pharmacist is interested in studying the relationship between the amount of a particular drug in the bloodstream and then the corresponding reaction time in seconds of those people taking the drug. 10 people were randomly selected and administered various doses of the drug, so from 1 to 8 milligrams, and then their reaction time in seconds was measured 15 minutes after that drug was given to them. So it looks like, as we go through here, as the amount of the drug dosage was increased, the reaction time got longer as well. So that would indicate we probably have a positive relationship here. X is going up, Y is doing the same thing. And the amount of drug would explain why the reaction time was responding the way it was. So X is independent or explanatory variable, and Y is our dependent or our response variable. And we can do equals correlation to find then the R value. So remember, order doesn't matter on this, but it will on the next thing. So I like to go Y first and then X. There's our positive correlation. And because it's really close to 1, that's a very strong linear relationship. Next, we're going to do the slope. For us, that's usually M. So equals slope for this one. Known Y's, here's where order matters. We have to do Y first, comma, and then your known X's next. It was a positive relationship, so it should not surprise you that that is a positive 2. If you look at our table, because this is going up by 1, we can see that this is about 2 each time. Not perfectly, but it's not a perfect linear relationship, so that's a good value. And then B is how we usually write the y-intercept. It is just called the regular intercept in Excel. So equals intercept. Again, known y's first, comma, then your known x's. So putting it together, what we generally write here with this, since this gives us our predicted y's, this is y hat. Okay, I'm actually okay if you just write y, but it is the predicted y's, and we'll indicate that as we go through here. But it's really the little hat, the caret above that y. And then our slope was 2.2381 x, the amount of drug, plus our 7.679. Okay, so that is our line of best fit. Okay, next one, they give us the line of best fit, and we're going to use it to answer a question. So suppose that a company wishes to predict the sales volume based on the amount of advertising expenditures. So looking here, the estimated sales depends on what advertising was spent. And here's our line of best fit. Sales manager thinks that sales volume and advertising expenditures are modeled according to this linear equation. And they're both in thousands of dollars. That's going to be important so that we solve here correctly. So looking at this, going back to kind of the relationship we were talking about up here, this is our slope and it's positive, and it's in thousands. So if you move that decimal 3 times, okay, you would get your 470 that we're looking with, $470 for every one. And then this here is the starting out amount, and moving our decimal again in terms of our baseline of sales values. Okay, so here it says the company has target sales volume of 175,000. How much should the manager allocate for advertising in the budget? So first thing we're going to do when we're given a problem is decide whether it's the x value or the y value in context. So we were given 175,000, and that for us is the target sales volume. So that's our sales. Then we look up here, and that would mean it goes in right here. So what I'm going to have you do is write down kind of the equation in pieces here. So the first number, I'll just go ahead and put an equal sign. So do a little apostrophe, so it reads it as text, and then the equal sign. Then over in the next cell, we'll put that 47.81. Over in the next cell, we'll put a plus sign. Again, I like to use that little apostrophe so it reads it as text. And then the next one is my 0.47. And lastly is my advertising expenditures. And that generally is where our X goes. So now we have this equation set up for us. We've got our sales volume number equal to this, and that lets us solve. So when we talk about solving for this X, the first thing we want to do is add or subtract over. So our first thing is getting rid of that. So directly below this, you're going to do equals, grab that number, and we're going to subtract off that constant. Now that is equal to, again, apostrophe there, only this part is left. Okay, so if you want to just copy it, you can paste it down. Okay, from here to solve, we just have to divide by that number. Okay, so equals. And of course, one other thing we have to do is remember that this 175,000 was in thousands, this was in thousands, and this was in thousands, and right now they're not consistent. An easy fix to that is changing this one right up here. If I move that decimal 3 places back, it just looks like 175, and everything auto-updates for us. Okay, so then it says the sales manager should allocate this much for advertising. So the sales manager should allocate 270. Remember, this is in thousands, so I'm moving my decimal back. We could have moved these 3 decimal places over as well, timesing them by 1,000 each, and then we wouldn't have to worry about converting. The only reason I changed that first one is so that I'd only have to change one number instead of 2. You get to pick your favorite. So they should allocate $270,617 for advertising. And that's it for that one. I may also give you a situation where I give you the advertising expenses, and that would be easier because then you just plug it in here. Then use Excel to find those values using cell select. Okay, last thing we're going to do is talk about scatter plots. So one more, technically a couple more vocab words. This first one is total of sum squared, and this is different from the sum of squared errors because of what we're subtracting. So here, if you look at your notation, you're taking the value minus the mean and squaring it, doing that for each of the values, and then adding them all up. Okay, so here, the total sum squareds, we are calculating by first looking at the value from our y mean. So to start out with this one, it says, oh, no context up here. So this is our situation from above, the amount of drug and the reaction time in seconds. Okay, the average reaction time we know is going to be somewhere between this 10 and 26. We can easily calculate it just by doing, let's do y bar over here, equals average. And then of your y's, the reaction time. There it is. So in order to do our difference, we would take y minus y bar, so equals, grab your y value, minus our y bar that we found, and drag it down. Okay, just like last time, we need to square those. Okay, let's move these over to the side. Do a Control X, move them over here, Control V. We'll come back to those. And looks like I have to refill down. For this one, I did not get my cell select. Okay, let's restart that one. Alright, equals, starting with the y value minus this, and we want to keep that locked in. Do your F4 to freeze that, and then I'll re-drag it down. There we go. Okay, so that gives us a distance each of these is from that average value. Then we square them. Cell select, squared, and drag down. And just like the sum of squared errors, we're then going to add them together. Equals sum. For that value, 213.5. Okay, so Hawks asks for this sometimes, but really the bigger detail is not really finding this sum. It's talking about what's called the coefficient of determination, which is r squared. That's why I had these values r and r squared, because r squared, even though it's capitalized, is literally our correlation coefficient squared. And the relationship to it, I'm going to talk about this one, is 1 minus the sum of squared errors, what we did a little while ago, divided by the total of the sum squared, sum of squares that we just did here. Okay, so we're going to do our equal correlation again. We already did this one, but we'll just bring it down again for practice. Doesn't matter the order, but our original numbers here. And then our next one. And that, we said, was a strong linear relationship between our amount of drug and our reaction time. If we take that value and square it, we'll get the coefficient of determination. And what that does is talks about the variation that is in the y values that is explained by the model. So the formatting for this interpretation sentence is down here. You're going to say the estimated model, okay, ours is going to be the line of best fit always. So we can say the line of best fit accounts for about, and we'll change it to a percent, okay, because these values are 0 to 1, and it really talks about the proportion of the variation. So here, you're going to do your equals and just grab that number from up above here. And looks like it's not calculating as a percentage like I want it to. I formatted it as a percent for you already, but it's a little bit off. So we're just going to do that again. Equals r squared. And there's the percent popping up. I'm not sure. I think my Excel is off by a value, so yours should have worked the first time. Okay, so what I want you to add below here, your estimated model is always going to be the line of best fit. And over here, this variation in reaction time for us is going to be whatever the y context is for any situation. So you can always write it in this format just by changing that r squared value to a percent. So not only was this very strong, in fact, 98.5% of our variation in the y values in the reaction time was taken care of by that line of best fit. Okay, almost all of it. Okay, so now we're going to kind of put things together and talk about scatter plots. Okay, so first example here, it says the table below gives the age and bone density for 5 randomly selected women. And we're going to find the line of best fit for predicting a woman's bone density based on age. Okay, so that tells us right there that age is predicting our bone density. So age is our x value, and bone density is our y value. So first thing it asks us to do is find the slope equals slope here. Y is first. That's why it matters that we know which one's which, and then our x's. Okay, that means as age goes up, the bone density is going down. And a lot of times I'm going to have you interpret this, so let's practice for that. We would say each year a woman ages, her predicted bone density decreases by about 1. And I don't believe they told us what bone density was measured in, so that's all we would need there. Okay, but here's what I did. This number, I'm putting over 1. Okay, so this -1 is telling me about increasing or decreasing for whatever y is. And then you're going to always say each one, whatever the x is. So that was each year a woman ages, and then her predicted y value goes up or down by whatever that slope is. Okay. Estimated y-intercept, that's our b value, and it's equals intercept, remember. Known y's first again, comma, known x's. That just means the starting point for like someone aged 0, which probably does not apply to this pattern because 0 is way far away from these values in our set. Okay, so this, just write in the answer. We're not going to worry about interpreting that necessarily. It says determine if the statement not all points predicted by the linear model fall on the same line. Okay, so we want to decide if that is a true or a false statement. So it says not all points predicted by the linear model fall on the same line. Okay, the predicted points are the points on the line of best fit, so this is false. Now, if I asked you not all of the points fall on the linear model, that could be true. Okay, we don't know how good this linear relationship is, but this said not all points predicted by the linear model fall on the same line, and that's literally how we make a line of best fit, is putting predicted points and making a line. Okay, so that was false. We're going to find the estimated value of y when x is 60. In order to do that, we have to use both our slope and our y-intercept. So let's start by writing our equation of our line, kind of like we did that last time. So it's y hat, or just y is great. Then apostrophe equals, grab your value up above of your slope. Okay, and then here's our x, apostrophe plus, and then our b, grabbing from above. We already did the work for it. So there's my line of best fit right there. It says find the estimated value of y when x is 60. So we're plugging in 60 here. So we can do that all in one go. Times 60. Let's actually just put 60 here for a moment so you have those notes, and we'll just do it below. So equals that times 60 plus our y-intercept. So the predicted bone density is this 321. Again, this would be something that you would label if we had context. So this is the predicted bone density for a woman aged 60 would be about 321. Okay, and that's very close to our table value. That was 323. This one, it says substitute the values in step A and B to find the equation for the linear model. and according to this model, if the value of the independent variable is increased by 1, find the change in the dependent. Okay, so this first part is this we already did. Okay, so we'll just copy that and paste it down. So this is our model. I'm going to repaste it. Do this with me. You do a control copy. And then when you right click, there should be a paste special where you can paste only the values. And if you click on that, you won't get the error. Or you can always retype it. This one just wants the model, so you can write it all in one go. You don't necessarily have to do it in separate cells. The separate cells only helps when you're predicting things like you did up here. Then it also said, according to the model, if the value of the independent variable increased by 1, find the change in the dependent. The second thing just says interpret the slope. And we did that on part A. Okay, so we don't need to do that again. Last part here, find the value of the coefficient of determination. Remember, that is r squared. So we need to find r first. Okay, so to the side, we're going to do equals correlation coefficient. That's r. Go back up to our values. Doesn't matter the order for this one. I'm going to do y first, comma, then x. Okay, we have for this one, relatively strong linear negative relationship between the two variables. And then now we're going to find r squared. So equals, grab that, and square it. And we're going to interpret. This says 3 decimal places, but I do want it as a percent. So click on that percent button. And then we'll add our 3 decimal places like they asked. So this would say the line of best fit accounts for about 89.375% of the variation in women's bone density. Okay. Last thing is we're going to put all of what we did together on a graph. Okay, so here we've got a situation where Paramount elliptical machines are giving, these machines are giving the heart rate during exercise. Okay, based on the age of the person, we're given the different heart rates on this elliptical. So as we increase the age, the heart rate is decreasing over here. Generally, there is a couple points in here where it's not perfectly the same number each time, but it looks like it could be linear. So the first thing we're going to do is create a scatter plot. It says let age be the independent variable. So that's our x, and the heart rate is our y. Hopefully that makes sense even if I didn't tell you, because age would in here explain why heart rate is responding the way it is. Okay, so what we're going to do here is I'm going to show you a couple ways to do this in terms of some of the pieces that we've already talked about. So go ahead and highlight our table here. Sometimes when you highlight the title, it gets messy, and sometimes it requires you to highlight the title. Kind of depends on whether the cells are split or not. So here, I'm just going to highlight these values, and we're going to do insert. A lot of times the recommended chart works, but we're doing the scatter plot. So right here. And then we're going to add the context. Okay, so it wanted X and Y the way they are. Looks good here. This is talking about, if I add the title, the heart rates of people exercising on an elliptical machine. By age. Okay, So I'm looking for context, but also the X value and the Y value label at some point. Then what we're going to do is click this chart area. If you hit the plus sign, you can add on the axis titles. So our bottom was age in years. If you double click over here, our y-axis was referring to heart rate in beats per minute. And the last couple things we're going to do is adjusting with the points itself. So one thing that's different with two variable analysis versus one is we actually don't want all this extra space. When we were talking about one variable charts like the bar graphs, we didn't want to cut off this y-axis. We are allowed to do that with scatter plots because we're not talking about the pattern between growth one or the other. It's the association between the points. So I really care about just making sure that these points are the highlight or the center of my graph. So we can double click on the axis itself, and then if this doesn't pop up over here immediately, you can always go to the little bars, but we're going to change this axis to get rid of anything extra. So if you go to your axis options, it has these set up minimums and maximums, and we don't necessarily need to have 0 all the way to 100, but we don't want to start on 20, so maybe 10 to 100 instead. Okay, so we can start our minimum at 10 instead, and that's going to left and right take care of extra space. And then we're going to double click on the y-axis. Okay, and we're going to do the same thing. This one goes 0 to 180, but our lowest value is a little over 100. So maybe we want to go 80 to 180 instead. And it auto-fit this one to 170. That looks fine. If you want to change it back to 180, you can. Okay, but that gives us a better picture of the points, and we can see more clearly what's going on. Now this looks very, very linear. The last thing we're going to add on here is actually the trend line. The line of best fit is an option here. So if you click on this trend line, it will pop up as that line of best fit. And if you go over to the error, you can go more options and add in the label to it as well, and we're going to. So once you hit that more options down here, you want to display the equation on the chart, and you can also display the r-squared on the chart. So then dragging this out of the way, we have a complete scatter plot. Now all of these things that we did are going to be in the directions of formatting the graph to make sure things look nice. Okay, so I will tell you add axis labels, I will tell you to change the the scale so that the points fit. I will tell you to include a title and the trend line. So all of this is going to be on there, the instructions, to make sure that you remember all of that. Okay, then it says from here, I'm going to go ahead and close out of this so we can see it a little better. Maybe. There we go. Okay, so from our chart, we're going to identify some things. It says identify the slope of the line given by the display. Okay, so the slope from what we just did was negative 0.8321. If we calculate that with Excel, it's going to be the exact same number, but they may not show as many decimals on the chart. So that's the benefit of calculating it by hand, is we have more accurate information. So if we're making predictions, this version is going to be better, just using Excel versus using what shows up on the graph. Okay, what does it tell us in context? So this is good practice. So again, it's this number per 1. So this number for our Y is talking about heart rate, and it's per 1, again, years for this one. So as the age of the person working out increases by 1 year, the heart rate decreases by about 0.8 3 beats per minute. And I just rounded to do 2 decimal places by chance. You can really, if I don't tell you what to round to, pick whatever might be appropriate. I didn't want to round to 1 BPM because that's a little bit further than I'd like. But really what I require in here, remember, is you're going to talk about X, and then it's really the predicted heart rate, because the actual heart rate, you know, is going to depend on the person, but this is prediction based on what we have given to us. So context for X, context for Y, in whatever order you want, and then words that mean increases and decreases. So each year would mean increases by 1, that's happening here, and then slope is going to tell you increase or decrease for your other variable. Okay. The y-intercept that was given to you was 177.14. If we calculate that, it's equals intercept. So known y's first, comma, known x's, and it adds extra decimal places. You can even add more decimal places, so remember this is more accurate than the one on the picture, okay, because if we're doing cell select, it's going to get all of those in place. Then it wants us to calculate R based on the R squared given on the display. So based on this, we would do square root of that 0.994. So our value that looks like that. And we're going to compare it to the correlation version with Excel. Going back up here. Doesn't matter the order for this. Okay, close, but not exactly the same, especially when you get to those in decimals. It's usually close enough. Okay, just showing you more than one way to find this. Okay, I'm going to default to the Excel formulas, but there is a backup of having it on there. I will have you add those features to the graph anyway. What does R tell you about the two variables? So if we're interpreting, since R is negative and close to -1, there is a strong, because close to -1, negative, because negative, linear relationship between age and heart rate. I do want to see context here, okay, but you can, this one we're putting it together in one sentence because we know what each one represents. The value of R squared is given on the display. Use Excel and your calculator value to calculate. So we did R squared, but now we're going to use our R value and see that 0.994 from up here. Okay. Says explain what this tells you. So in context, about 99.4%, and I'll go back up and change that to a percent because I am going to require that of you, of the variation in Y context, so for us, heart rate, is explained or accounted for the line of best fit. So just to show you, you can write either version in terms of order. Back up here, just hit the percent button for me, and we're good to go there. It says use your trend line to predict the heart rate of exercise for a 35-year-old. Okay, so 35-year-old, going back up here to these pieces, we're going to just put it all together up here. So there's my Y equals the slope X plus, and then the B value. So we want a 35-year-old. A 35-year-old is X right here. Just plugging it in. So equals that times 35 plus our y-intercept. So it looks like a heart rate about 148. Beats per minute. Okay. All right. This last one says, consider the monthly sales data for technology company for a 12-month period. Here's the context of it. What I want to do is just talk about how this would look, not actually calculating things. So as the months are increasing here, our sales in thousands looks like they're going up, a little bit of going down, then up again. So we may have a less strong positive relationship, but it'll definitely be positive. Okay, we can calculate correlation coefficient, we can insert the chart. Okay, what I want to do is talk about prediction. So this last little piece of information here is vocab. Interpolation is where we are using a prediction to model something that's inside our values. So back up here, when we predicted the age for a 35-year-old, since 35 was in our known values, from the lowest value of 20 to our highest value of a 90-year-old, it'd be considered interpolation, which means we can use our line of best fit to predict that without much worry, assuming that a linear model is a good fit. But if we ask to find a prediction for like a 10-year-old, okay, kids are just wildly different, and we have no data on them that was built into this model, which means their prediction may not be as accurate. So that's considered extrapolation. So that would be outside. So here, if we're looking at months, we are looking at sales data for a 12-month period. If I wanted to make predictions for the following year, maybe 20 months down the road, we can't guarantee that the same trend that happened in this year would continue for the next year. Okay, so we want to be careful with those types of predictions because they could lead to misleading results. Okay, what I want you to do here is try this extra practice problem if you have time, just with your scatter plot. Not necessarily necessary for all of the pieces, but making sure that you're practicing with that insert chart, knowing where to adjust all of the features, practicing playing around with the plus sign to add in your axis titles and all that stuff. But then your homework is on Hawks, and you can always come see me with questions.